Alright, ladies and gentlemen, this is our video to going over our practice test that I gave out in class. Also, you could get a copy of it through PupilPad. Just download it. It's on a PDF and print it out for yourself. There are 35 questions on this. It's going to be a very calculation-based test. So, with a few concepts thrown here and there, so I hope it doesn't become too draining for you guys. So let's begin. The first topic we're going to go through is a series of work questions. And the first one we're going to start with is this graphing question. So which graph best represents the greatest amount of work? So work, we should know, is W is equal to F times D. And if we're looking at a graph, that means we could find this on the area under the curve. Okay, so we're looking for the graph which has the most area under the curve. If you guys take a look at each of them, it's got to be choice B. If you also do the math, for example, our force here is 8 newtons times our distance of 0.5 meters, and that gets you 4 joules. And you do the same for each of them. For A and C, it's a triangle, so you got to do 1/2 base times height. So 1/2 8 times 0.5, and that'll get you 2 instead. Alright, number 2, through what vertical distance, so we don't know what D is, they gave us the force of 50 newtons and the work of 250 joules. So work is equal to force times distance. You find that 250 equals 50 times D. D is equal to 5 meters. B. Alright, number 3. How much work is done on a downhill skier by an average braking force of that many newtons to stop her in a distance of 10 meters? Same thing. Alright, that is about 980 newtons times 10 meters. That should get you 9,800 joules. That's choice D. And then number 4, same thing, 20 newtons, 5 meters. The mass of the car you don't need at all. So work is equal to 20 newtons times 5 meters. You should get 100 joules. Okay, now number 5, I might have said the wrong answer in class because I was too quick to read this. I only looked at work measured in. Well, that would be joules. That is work. But the question has also asked the rate at which work is done. That means we have to take work over time. And what does that equal? Power. And what's power measured in? Watts. So the correct answer for that is actually D. I apologize, guys. Alright, so number 6 is asking, as the time required to do a given quantity of work decreases, the power developed, what does it do? Okay, what happens? Time is going down, so what happens to power? If we notice, power is equal to work over time, so we divide by time. So that means, if you also think about it logically, less time equates to more power. So the quicker someone does it, the more powerful that person is. So power developed increases. Number 7. A small electric motor is used to lift a 0.5 kilogram mass at constant speed. If the mass is lifted a vertical distance of that in 5 seconds, what is the power? Oops, okay. That's our mass. Distance of 1.5 meters. T equals 5 seconds. Looking for P. But notice here they gave us a mass. So that means we got to convert that mass to newtons by doing 8.5 kilograms times 9.81 meters per second squared. If you want to turn it into newtons, so that's half of 9.81 is 4.905 newtons. Okay, so now we could go into our definition of power, which is work over time, which is also equal to force times distance over time. And so you should get 1.5 watts as your answer. Now next is number 8. What is the maximum amount of work that a 6,000 watt motor can do in 10 seconds? So they gave us power, 6,000 watts. They gave us time as 10 seconds. And we're looking for work. Definition of power is work over time. So we're looking for W. So you get 6,000 equals W over 10. You get W is equals to 60,000. So that's choice 4. D. I am not in the best mindset today, guys. I apologize. Alright, number 9. They gave us 58,000 watts as our power. And they gave us the force is 21,000. And we're looking for velocity. So what kind of definition of power is that? So I'm going to write it over here. P is equal to F times V. That's a new definition. Because if you notice over number 7, where I wrote FD over T, D over T happens to be velocity. So you could do F times V as another way to find power. So we're going to do 58,000 equals 21,000 V, and you get V should equal 2.8 meters per second. C. Number 10 is another kind of power question, in which probably is one of the more difficult ones. They gave us P is equal to 20.4 watts. Mass is 5 kilograms. And time is 10 seconds. We're looking for distance, height. Alright. So, power is equal to FD over T. On the side, you should change that 5 kilograms to newtons by multiplying about 9.81. And you should get about 49.05 newtons. Okay. So now we could do 20.4 watts is equal to 49.05 newtons times our D, which we're looking for, over 10 seconds, and you should get a D is equal to 4.16 meters. Choice C. 11 is just like 10, same idea, this time looking for power. So as our shortcut, I'm just going to take our mass here, 2 kilograms, multiplied by 9.81, just do it all in one go in the setup, times our distance of 15 meters over 6 seconds, and that should get us 49 watts. Now be careful here if you look at choices C and D, same number, but power is watts, joules is work, different things. So be careful there when you're looking at the units. Number 12, if the direction of a moving car changes and its speed remains constant, what quantity must remain the same? So we could cross off momentum and displacement. I've noticed that a lot of you were stuck between A and D, velocity versus kinetic energy. Now see here, velocity is a vector. Kinetic energy is a scalar. Now, if you think back to the definition between vectors and scalars, vector is dependent on direction as well. Now, if the direction is changing, you don't have constant velocity. So that means the only thing that's constant here is kinetic energy. It's a scalar, it doesn't depend on direction. Okay, 13. Compared to the kinetic energy of block A, the kinetic energy of block B is, so I suggest you go about this problem using dummy variables. You plug it in. So let's look at A. Kinetic energy of A equals 1/2 mv squared, so has 2m, and the velocity here is just v. Okay. So we just get mv squared. Now let's do for kinetic energy of B. Same thing. So 1/2 m 2v squared. Now notice here v is squared, so that's going to be a 4v squared. 1/2 m 4v squared. And that's going to get us to 2mv squared. Now if you compare both of these, you double it. So block B has twice the amount as block A. What affects it more is the velocity, because why? Velocity is squared. Now number 14, let's pick a different color. Okay. As an object moves upward at constant speed, its kinetic energy what? Alright, keyword here, constant speed. If speed's constant, that means kinetic energy is also constant. Alright, 15. As a bullet shot vertically upward rises, the kinetic energy of the bullet must... Alright, it's going up. What does it do? It slows down. So the kinetic energy, as a result, will also decrease. Now number 16, 75 kilogram bicyclist coasts down a hill at a constant speed of that. What is kinetic energy of the bicyclist? Once again, 1/2 mv squared. 1/2, our mass is 75 kilograms. Our speed here is meters, 12 meters per second. Do not forget to square that. So it's 12 squared. And you should get an answer of approximately 5,400 joules. So that's choice C. Alright, number 17. If the speed of a moving object is doubled, the kinetic energy of the object is... Alright. So let's just go look at our normal kinetic energy. Just that. Plug in 1 for everything. And you get just 1/2. Now what happens when we double that speed? Keep the mass the same. This time you'll get 2. Now what happened here? What kind of change happened? It was 4 times as much. Quadrupled. 2 squared, you should get 4. If you triple that speed, it should be 9 times greater. Quadruple the speed, 16 times greater. So it's a squared effect. Number 18. Gravitational potential energy with respect to the Earth is dependent on the object's position. Potential energy is equal to mgh. Okay, 19. Oh, now we're talking about this. How do we decrease the gravitational potential energy? Since it's dependent on height, if we want to decrease it, you want to decrease the height. The only one that fits that is choice D, jumping down from a tree limb. Number 20. This time we're calculating for potential energy. Okay. 75 kilograms times 9.81 times 3 meters high. And you should get choice B. Approximately this much joules, I believe. The only one that fits that is choice B. Now let's look at 21. Okay. Object weighing that much newtons is lifted from the ground to a height of 0.22 meters. Increase. You could look at it this way. The work you do can also change an object's potential energy. So the increase in potential energy is equal to F times D in this case. Or you could do MGH. They already gave you MG as 15. 0.22 meters. You should get 3.3 joules. Alright, number 22 is tricky because you need to do two equations. Okay, because they gave you K and they gave you F. And we're looking for the potential energy in a spring. But we don't know what X is. We need to know what X. So let's look at the force in a spring to solve for X. So 1.2 is equal to 4x. You should get that x is equal to 0.3 meters. That's how much you compressed the spring, by 0.3 meters. Now the second part of this question we have to do is finally solve for PES using x. Because notice here, this is the equation for potential energy in the spring. 1/2 kx squared. We have k, but we don't have x. So now we do. Okay, 4.3. Do not forget to square that, and you should get 0.18 joules. If you forget to square it, then you'll probably get C. So don't forget to square that x. Alright, 23. So here they gave us the kinetic energy of the spring, which is 16 joules. We're figuring out what's the spring constant of spring. So all of that kinetic energy of the cart goes into the spring. So that's now potential energy in the spring to compress it. Okay, now we could figure out what the spring constant K is. And how much it compressed was 1 meter. Okay, now we can figure out that K is now equal to 32 newtons per meter. Choice A. 24. Looking once again, PES equals 1/2 kx squared equals 1/2, our K they gave us is 80 newtons per meter. Displaced 0.3 meters. That's how much x is. Don't forget that's squared. That's now equal to 3.6 joules, choice A. Number 25, as the spring is stretched, its elastic potential energy. Okay, so stretched meaning x goes up. So if you notice in here, if you increase x, PE also goes up. Okay, so also think about if you stretch it or even compress it together, it has more energy starting to build up into it in order to release back into its original position and probably cause some work on another object. So there is increasing. So the more you stretch it or compress it, the more energy it will build up. So let's move on to 26. Okay, how much work must be done to stretch the spring 0.4 meters? So here we know that have another force distance graph. So work, once again, is this shaded area. Find the area of that. And because it's a triangle, it's 1/2 base times height. Our base here is 0.4, and our height is 24. Okay. So now you'll get about 4.8 joules, choice A. Alright, 27. What is the spring constant for this graph? Okay, so once again we have the same type of graph, force versus distance or x. Okay, finding the area by multiplying them together gets us work. On the other hand, if you take the slope, change in y over change in x, we have force on the y and x on the x. What does that give us? If you look back at this equation, Fs equals k times x, Fs divided by x, that gets us k. So the slope here equals the spring constant k. So greater slope, greater k. Now we got to find the slope of this. I'm going to pick these points over here from 0, 0 and 1 point over 0.4. So my change in y over change in x is going to be 1 over 0.4. And you should get 2.5 newtons per meter. Choice B. Number 28. Okay, we're looking for force to stretch a spring. So this is this equation. We got our spring constant K of 25 newtons per meter times our compression or stretching distance of 0.25 meters. So 0.20, so 25. What is a quarter of 25? That's about 6.3 newtons. Choice C. Alright, number 29. Finally, we get to talk about pendulums. Yay! Alright, which statement is true about the swinging pendulum? So let's see here. Pendulums. Here we have points A and C. They're the peaks. You know what they also have? The maximum potential energy. Why? Because they're at the highest point of the swing. Now point B is, I would say, equilibrium position. So that means at that lowest point, we have the highest kinetic energy. So conservation of energy says potential energy converts to kinetic energy and vice versa in order to keep the total energy of the system conserved. So they go back and forth between each other. So let's look at our statements here. Potential energy at A equals kinetic energy at C. That is incorrect. B, speed of the pendulum at A equals the speed of pendulum at B. Incorrect. Potential energy at B equals potential energy at C. Incorrect as well. Potential energy at A equals kinetic energy at B. That is correct. Because notice here at the peaks, max potential energy, which then converts all the way to kinetic energy at the bottom. All of that goes from one form to the other. Now number 30. As the pendulum moves from the bottom of its swing, so going from B to the top of its swing at either A to C, so B to A or B to C, that means our potential energy should increase while kinetic energy goes down. Because of height, potential energy goes up because of height, and kinetic energy goes down because it's slowing down. So it's choice D. Number 31. Actually, we should answer 32 first. So I'm going to do 32 here. You might not see it. I hope you guys have the paper on you. But it's asking for the kinetic energy down here at B. So the block starts at point A and it slides all the way down to B. And we need to figure out what's the kinetic energy down there. Now if you know, here at the top we have max potential energy, which always converts into max kinetic energy at the bottom. So we should know that the max potential energy at top should equal to max kinetic energy at bottom. Oh, I'm getting a message. Alright, so what is the potential energy here? mgh. Max kinetic energy, we don't need to actually expand it out. Okay, so 10 kilograms times 9.81 times our height of 5 meters equals kinetic energy. You guys should get 500 approximately joules. Now this will help us solve for 31, in which now Ke can expand to 1/2 mv squared. You're going to use that kinetic energy to finally find the speed at point B. 10 v squared. Okay, and you should get that v is approximately 10 meters per second, choice B. Okay, finally the last slide here. Choice D, I've already said in the previous slide. Now number 33, another conservation of energy problem. So here it tells us that an object strikes the ground. It's falling, just about to hit the ground. And so its kinetic energy down here is 1960 joules. Know that up here at the top where it started should be its max potential energy, should also equal the same thing due to conservation of energy. Okay, and we gotta figure out how high above the ground it was. So knowing that potential energy is mgh, we could finally figure that out. 20 kilograms times 9.81 times h, where h is now equal to, should approximately 10 meters if I'm doing the math correctly in my head. Yep. Choice A. Alright. Number 34. A car uses its brakes to stop on level road. So I'm underlining level road. That means, or I'm not going to write it out here. Okay. So that means the potential energy doesn't change. There's none. We have no height change. So we could cross off C. We could also cross off B because we're not working in that realm. And light energy, we haven't even talked about that yet. So that leaves us with internal energy as our answer. But why? If we actually think about reality, total energy is equal to all of these things. Kinetic energy, potential energy, and internal energy. Now this here is friction, due to friction. Internal energy is due to friction and sound. That's the reason why when you bounce a ball, it doesn't reach back to its original height, because it loses energy to both friction and sound. And it's the same thing with a car braking. You hear a sound, and it's also friction being involved. So a lot of that energy there is being converted, all of that kinetic energy here is being converted to internal energy. Now we're on the final question here. A child starting from rest at the top of a playground reaches a speed of 7 meters per second at the bottom of the slide. What's the vertical height of the slide? Okay, same thing. Oh, okay. They didn't even give us the mass of the child. Well, we don't actually need to calculate for the mass of the child, to be honest. So here, know that at the top, here should always equal to the kinetic energy at the bottom. You can use Kp equals KefPef, or you could just go about this shortcut here. Know that these two are equal to each other. So that's why they didn't give us the mass of the child. Because you could set these two equal to each other and know that masses will cancel out here if you divide by mass on both sides. You could solve for h this way. And so you should get that h is equal to, should equal to 2.5 meters. So that's choice C. Okay, so that's the end of that video. I hope this was helpful for you guys. I'm pretty sure I covered all the topics that are going to be on this test. If I were you, I'd focus a lot on that internal energy, mechanical energy, potential, kinetic energy stuff. Some springs, some work, some power, but definitely conservation of energy with kinetic, potential, internal. Just so you know. Good luck, guys. Don't study too hard.